Hi, it's Pauline here. So today we're going to have a go at this question. Prove that tangents to the parabola at the extremities of the focal chord intersect at right angles on the directrix. So if you're not terribly clear on the terms we're using here, then have a look at this activity. But otherwise, let's get started. So here we've got our standard form parabola, x squared is 4ay, and we've marked the point 2ap ap squared, which is one end of the focal chord. So let's call that p. And the other end of the focal chord is 2aq squared, and we'll call that q. And the focus here is at a distance a from the vertex, so that's 0a. And the directrix is also at distance a from the vertex, and it will be y equals minus a. And this is always the case for our standard form parabola, x squared is 4ay. And so the question is asking about this intersection. We want to prove that the tangents at p and q intersect at right angles on the directrix. So, well, what do we know about these tangents? Well, the equation of the parabola is x squared is 4ay, and we can rewrite this as y equals 1 on 4a x squared. So to get the gradient function, we'll just differentiate this. So dy dx is 1 on 2a x. So now at point P, the x value is 2ap, right? So the gradient is going to come out very nicely as P. And at point Q, the x value is 2aq. So the gradient is Q. And again, it is a bit awesome that the gradient at every point on the parabola is actually the value of the parameter at that point. So now let's look at how we might relate Q to P. And here we know that PQ is a focal chord. So let's work out the equation of the line PQ. And we'll start with its gradients, which is just rise over run, right? And so let's tidy that up a bit. And there we have it. The gradient of PQ is P plus Q all over 2. And now we know that the focal chord goes through the focus, which is 0a. So we'll use our standard form for a line, which I always think of as y minus y1 equals m times x minus x1. And we have y1 is a, and the gradient is p plus q over 2. Now, x1 is actually 0 here, so it'd be like this, but we don't need to fill it in because we're like subtracting 0, right? So we also know that the focal chord goes through 2ap ap squared. So if we substitute that point into this equation, it will be a true statement. So let's do that. And now we have ap squared minus a equals p plus q over 2 times 2ap. So let's divide that through by a, right? And then we can tidy it up. And this gives us p squared minus 1 equals p squared plus pq. So that's very convenient. This comes out very nicely as pq equals minus 1. And we've already figured out that the two tangents have gradients p and q. So if pq is minus 1, then the tangents must intersect at right angles. So we've done that first bit. Okay, the other thing we want to know about the intersection is whether or not it is on the directrix. So that's like finding out if the y value for the intersection is minus a. So first we'll do the tangent at P, and again we'll put it in our standard form for a line, and this line goes through 2ap ap squared and has gradient P. So we'll tidy that up, and that comes out as y equals px minus ap squared. And because we want to find the y value for the intersection, let's rearrange this equation to be x equals y on p plus ap. And we'll have a similar looking equation for the tangent at q, right? So x equals y on q plus aq. So for the intersection, the x values are the same. And so y on p plus ap equals y on q plus aq. Now, we worked out earlier that pq is minus 1. So q is minus 1 on p, and we'll sub that in. And we've multiplied that through by p, we'll end up with y plus ap squared equals minus p squared y minus a. So collecting y's, we get y times p squared plus 1 equals minus a times p squared plus 1. So that means y equals minus a, which is exactly what we were hoping to get for this intersection. So that's it. Hope that made sense. Thanks, guys.